Good afternoon, everyone. I think we're waiting for a few more people to join us. But it is a real pleasure to be here this afternoon, and thank you so much for joining us for the Arden Bemet Distinguished Lecture this afternoon. And we had a wonderful presentation earlier that was for our award in Humanities and Social Sciences on the lives of military families, and it was a really inspiring presentation. And I think prior to that, we also reflected on the fact that just taking a bit of time periodically throughout the year to reflect and celebrate on our tremendous accomplishments is just a wonderful opportunity. For those of you who don't know me, I'm Teresa Mayer. I'm the new Executive Vice President for Research and Partnerships, and I am just closing out 3 months in my position. I started on August 1st. I'm returning to Purdue. I was a graduate student here many, many years ago, and it has just been a very warm welcome back to Purdue. And it's really a privilege to participate in this event and have all of you gather to celebrate. I look forward to listening and learning throughout the lectures this afternoon, and I hope that you enjoy this event as well. This year, 2019, marks the 5th year for the Arden Bemet Jr. Award. This award was established by Distinguished Professor Emeritus Arden Bemet and his wife, Mrs. Louise Bemet, to annually recognize a Purdue faculty member for recent outstanding accomplishments in pure and applied science and engineering. The Arden Bemet Jr. Award winners are nominated by their peers and approved by my office as well as the president of the university. We are delighted to have Distinguished Professor Bemet and here with us this afternoon in the audience, and I'd like to just spend a moment giving him a hearty round of applause for his support of this award. So again, thank you so much for your support and the support of the other alumni who have endowed awards for our distinguished researchers here at Purdue. At this time, I would also like to acknowledge any past Arden Bemet Award recipients who are attending the lecture today. So if you're here, I could please stand so we can recognize you as well. Wonderful, thank you. We will have a reception to celebrate this award recipient immediately following the lecture, and this will be held in Stewart Center's Robert Ringel Gallery, and it's just to the left down the hallway. So I hope you will be able to join us for some light refreshments after this event and continue to ask questions and engage in conversation after this award. So I would now like to welcome the nominator of our awardee, the Ann Burnett Distinguished Professor of Electrical and Computer Engineering, Professor Shalev. As the nominator of this year's awardee, he will introduce Professor Narimanov, who is a professor in electrical and computer engineering, as this year's recipient of the Arden Burnett Award. So, Vlad, if you could.
Well, I feel very special about this presentation for 2 reasons. One is obvious. Evgenii is a friend and truly outstanding scientist. I'll say more about this in a moment. The other one is Arden. Arden Bemet is a living legend, and I'm so proud to be one of your many, many friends. You're such an exceptional person. I mean, you're unbelievable. We're really blessed to have you with us. Thank you so much, Arden. Well, Evgenii graduated. He obtained his PhD in theoretical physics with honors, with highest honors actually, from the best school in Russia in physics, which is Moscow Institute of Physics and Technology. And then, after having a postdoc first in Yale and then in Bell Labs, he served as an assistant professor in Princeton before finally deciding to move to a better school, Purdue. So he had an NSF Career Award, he is OSA Fellow, he is IEEE Fellow. By the way, he obtained his IEEE Fellowship honor when he was an associate professor. I think it's kind of exceptional and unusual. Evgenii has truly outstanding background in theoretical physics, which helps him to work in so diverse areas, ranging from theory of chaos, nonlinear dynamics, to theory of lasers, to information theory. In all these areas, he actually did truly disruptive breakthrough-like works, which would stay in the history of science. But his biggest fame comes from the field which he pretty much established himself, so-called hyperbolic metamaterials. And the thing to mention here that literally, I mean, I do mean it, there are no conferences, major conference, national or international, in the area of photonics or optics, which would not run sessions on Narimanov's hyperbolic metamaterials. That's huge. I really, that's something to be proud of. I think he brings lots of visibility and pride to Purdue with his outstanding work. Well, some seasonal observations, Halloween-like. You might wonder why, with all his Evgenii's brilliance, we actually don't see him around much. There is a small secret. He works during nighttime. So, and when we work, he sleeps. So that's a simple explanation. That's when, during nighttime, then when all his disruptive great ideas come out. So I also should mention that Evgenii, as many truly talented people, is so broad. His encyclopedic knowledge goes far beyond just physics, theoretical physics. For example, his knowledge of history is just amazing. I always feel kind of handicapped when we discuss history. I mean, he knows it professionally. You'd be surprised, for example, he knows law. I mean, he could make lots of money by being a lawyer. Thanks God he decided to be a physicist. So anyway, as my colleague and beloved wife Sasha says, if you have a big, difficult question, consult Google. If Google cannot answer, ask Evgenii. So Evgenii is really a world-changing scientist and engineer. Please join me in welcoming Evgenii.
Thanks. All right, so how do I switch to my screen? Perfect. All right. So indeed, the story that I'm going to talk about today is the story of this hyperbolic metamaterials that has the potential to be a really major factor in development of photonic technologies in the next couple of decades, well, or so I think. But before I go after it, I would like to start my presentation with a quote from a rather brilliant poem from 19th century, Ulysses by Lord Alfred Tennyson. For my purpose holds to sail beyond the sunset. Somehow humans are born with this unbelievable, maybe unexplainable thrust for new knowledge, with this curiosity, this great desire to look, to see what lies beyond the horizon. During the age of discovery, that's what I think drove people to this unbelievable and imaginable and unimaginable danger of the heart of the Africa or the New World or to the icelands of the frozen continent and the South Pole. And as scientists, we're incredibly lucky that we can satisfy our thirst for new knowledge, for our thirst for discovery of what lies beyond the horizon in the safety and the comfort of our labs and computer rooms. And that's actually not hard at all. It's safe, and when doing that, we stand quoting from Sir Isaac Newton himself, we stand on the shoulders of giants. And it's not that hard once you're there. What is quite hard is the quest that comes before that, when they climb to those giants' shoulders. And many of us, those who actually do have real talent, don't make it. What makes the difference are the people who help you and guide you along the way. From your parents who who give you this idea that there's this wonderful world around you, and you can actually understand something that people didn't do it before. When, for example, they're showing you the pictures, which were just a few years back, taken by this Soviet moon probe Luna 3. It was taken in the 1960s, but for me, when I saw them first time, it was a few years earlier. Your mentor in high school who opens you the beauty of theoretical physics. The department head in the university who accepts you into the program, even though your entrance exam scores are not that impressive at all. And your advisors, research advisors, and all your friends. So to all those people, thank you. So let's start with this, and I'm going to keep this presentation simple and entertaining. Again, think about how complicated the molecules and the atoms are. You have so many atoms, and they can form so many different kinds of molecules. How come the world is so simple? Because what all they do, they really form one of three different things. Something that you can explain to a kid like that. I copied this. Oops. Let's see. All right. Now, is this better? All right, I'm going to use that. I have taken one of those children's books about this idea of solids, liquids, and gases, no matter what material it is. And when you study about electricity, it's also quite simple. More or less, they all are about conductors, which conduct electricity, and we call them dielectrics and insulators that don't. Very simple, despite enormous underlying complexity. Sometimes, though, the simplicity is slightly deceiving. What we now know is that not only do we have conductors and insulators, there is something else, what I call the third state of materials, the semiconductors. What they look like, at high temperatures, they look like poor metals. At low temperatures, they look like poor insulators. And it took some time to understand they are the third state. They are a different group of materials. And once this understanding came, the results were revolutionary. All our semiconductor electronics results from this simple understanding. What I'm going to tell you, and the story I'm going to tell you, that in the world of optical materials, in addition to the things which are so used in addition to dielectrics and to metals, in this case, this is the picture showing light. Did I just lose it? Right. In addition to those simple dielectrics and metals, whom we describe dielectrics with the dielectric permittivity and the square root. I just lost my pointer. Let's see. Usual thing is to do a restart. And it's still, I'm not sure. All right. I think we can still do it. So, but if there is a pointer, a backup pointer here, I'll appreciate it. So we have dielectrics, which allow the light to propagate, and we have metals which reflect the light. And the point is that in addition to those two, there is another possibility, the third state of optical materials that are different from either metals and dielectrics. Something that was hidden from the understanding of the scientists for quite a long time, just as semiconductors were. Again, this picture shows in the middle, there is a picture taken in the lab of Mikhail Lukin of one example of such material. If you look at that, it looks kind of similar to dielectric, but there is a difference. There is a difference. You can see that this dashed line, which shows the normal, the perpendicular line to the interface, and the refraction goes in the wrong way. That's the signature of the great things to come from there. But other than that, they look kind of normal. Well, what if you look at them? What if you look at different types of those materials, which I did not yet tell you about what they are? What they look like are sometimes dielectrics, like this a few examples on the left. A good example is something called hexagonal boron nitride. The material became very popular when people realized that it makes a very good substrate for graphene, for the two-dimensional materials. But it became very interesting in its own right. No, that should do it. If it's perfect, that's all I need. All right, so the day is saved. So that's the picture of hexagonal boron nitride. That's the sample. But something like simple alpha quartz will also show hyperbolic behavior in proper conditions. And even a gemstone, such as sapphire, will do as well. But they're not necessarily dielectrics. Graphite, bismuth, well, they look metallic, and they are metals. But they also show hyperbolic behavior. And this strange black-looking metallic object is actually a superconducting material, one of the high-temperature superconductors. That is also an example of hyperbolic material. They exist in the world around you, but were hidden for quite some time. And then you can also make them. This small piece is an artificial hyperbolic material. So to understand that story, to understand what's so different about them, why they were hidden in the plain sight for so long, you need to go back in time, back in history, and see how people understood light. It started from the ancient times when you notice that if you look at a beautiful picture on the forest like that, you see sunlight coming in straight lines. So this first idea, which survived all the way to the Renaissance, was that light is simply straight rays, straight, something that moves straight and allows you to see. Well, but then more experiments showed that you can in fact see something else, something that you cannot explain by simple motion of particles. If you have two sources of light in the proper conditions, you see that some areas will be brighter and some areas darker, the effect which was called interference. And Christian Huygens, in his Treatise of Light, gave a clear explanation of that in terms of waves that when overlapping on each other, when the crests of the waves overlap, you get more intensity. When the overlap with opposite signs, you get something close to nothing. But that was still confusing. And it got even more. Experiments by Erasmus Bartholin showed that you can actually see, and it's not really something that shows in unusual conditions, but if you take some of those crystals of calcite or some other crystals, and you look through them, you see double image. And it came up to Newton to form a coherent picture of the world, coherent picture of light. And our usual textbooks would say that he could not fully accept the idea of light being a particle, being a wave. And that was precisely the reason why. He could, at that time, when they were thinking about waves, they thought about sound, pressure waves. And pressure, if you think about atmospheric pressure, if you put your hand like that, the pressure here, or if you put hand like that, the pressure this way, well, they're the same. Pressure is a scalar. It doesn't have a direction. But clearly, something is different between the light that shows this image and that image. So to Newton, the explanation was that whatever forms the light, these things, they are something, probably particles, which have different sides. If it propagates one side first, it will form one image, the other side, the other image. And I want to emphasize, he did not take the full particle view. To him, the view was like that. Light is actually particles which have those sides, but particles which excite waves as they propagate an ether in the world around you. So believe it or not, this famous word of duality between waves and particles can be traced all the way back to Newton. Well, now we know a lot more than people did at that time. We know that electromagnetic wave is the signal wave of electric and magnetic fields. And the electric field has a direction, so it can, it's like this equivalent of Newton's sides of the particle for Newton. Can be, we call this direction of electrical field the plane of polarization. If it goes one way or the other, we can have different behavior. And the important feature of the wave, of this electromagnetic wave, is the period of these oscillations in space. We call it the wavelengths, shown here. And throughout the rest of the talk, I will talk a lot about this wave number, which is related to momentum of the wave, to pi over that. And this polarization is something that we can take great advantage of. And whenever, for example, whenever we see a fully three-dimensional movie. This technology is not that new. Comes from Edward Land and his Polaroid Corporation. We associate that with cameras. But the Polaroid Corporation was started in the 30s, and cameras showed up his camera showed up in the 40s. Initially, it was about the technology of controlling the light polarization, like making a three-dimensional movie when one polarization will be sending you the information for the one eye and the other for the other one. Back from the cinema screen into your eyeglasses, which have different polarizers, and then you see three-dimensional image. So that's how you can select it, but as for the explanation of the double refraction, in this case, you see the crystal of calcite, and you again see the double image there. Well, obviously, for the light polarized in one direction and light polarized in the other direction, you have different refraction, thanks to Snell. Interestingly, we all spell his name wrong. He was Dutch. It's not double L, it's a single L. But somehow, I guess the Latin spelling and the Dutch spelling got confused into Snell with double L. But the story is very simple. Different polarizations experience different refractive indices, and they go in different directions. Not surprising if you look at the crystal lattice of calcite. Obviously, vertical direction and the in-plane direction are so different, they will have different permittivities and different refractive indices. Fine. What if you have an isotropy? Before that, doing that, I will take the familiar equation from a, again, high school textbook and turn it into this form. I will really like this k² over epsilon fraction. You will see it later. That is nothing but the story of isotropic dielectric. So what if you have an isotropy? Well, algebra becomes much more complicated. Let's keep simple anisotropy, that z direction is going to be different from x and y, something like what we had in calcite. This direction obviously was very different in the crystal from either of those two, where the response was very similar. So in these cases, any undergraduate optics textbook would teach us, we have ordinary wave, which propagates with polarization in the xy plane, and the electrical field in the xy plane. So this wave does not know about what happens in z direction. It will only probe the permittivity in the xy plane. So it's not different. Same equation, same physics for ordinary wave. And from that moment on, I will forget about ordinary wave. We will focus on the other one, the extraordinary one. And for that one, the electrical field is not in the xy plane. So this field has two components, and obviously the equation which describes its propagation will have both permittivity in the xy plane, epsilon x, and the permittivity in the z direction. Mathematics, algebra, don't worry about it. I will try to confine it to the picture presentation. So to make a picture, to represent this algebraic equation, what we draw is the line which corresponds to this equation for fixed frequency. So we have kx, kz plane. So for isotropic dielectric, same number here, we get a circle. For anisotropic dielectric, for ordinary wave, the green one, we have the circle. And for extraordinary one, well, we have an ellipse because now the permittivities are different, the behavior in different directions is different. And you can use it in great many applications, like polarization light microscopy, where you rotate a polarizer, and the light which goes through isotropic material gives the same part of the picture, but light which goes through anisotropic material starts to go differently. So by looking at the difference of the picture that you see in the microscope, you can see which parts are isotropic, which parts are anisotropic, and then you can, and if you're looking at, for example, at a biological cell, you know which one it is, you can get a better idea of what happens inside. It works great for electrical for semiconductor chips, because some elements are and some are isotropic and some are not. But that was something which is very powerful, which used the fact that those permittivities are very different. And here's the thing. If you have an isotropy, why does the material in both directions have to be dielectric at the same time? What if the material has so much anisotropy, like this structure, which is made out of metals and dielectrics, the dielectrics shown in yellow, and the metals are shown in blue? Obviously, there will be conduction of current this way, but there will not be current conduction in the vertical direction. So something like this will have this great anisotropy. So what will happen? Well, your light will get really confused. The vertical polarization will tell you that we are in dielectric and we can happily propagate. This one will notice negative permittivity, and according to this part of the electrical field, you are in a metal and you can't propagate. Right? So reminds the story, the parable of the elephant, about blind people trying to determine, who can only notice the shape of the object. If they try to get an idea of an elephant, one will, who holds the trunk will see it as a snake, and the other, who holds the leg, will see it will think it's a tree. It's neither a tree nor a snake, obviously. So it's something else. So here, if this is permittivity, in those permittivities in those two directions, negative part will show metal, positive will be dielectric, and those two are this uncharted, unmarked territories on the map. Something where in medieval times you put a surprising picture and write there be dragons. Well, what will be those dragons? Well, we just take this equation, which I showed you before, and draw what it means, and it means hyperbolic shape. Right? So what's the big deal? It is a different shape, it is a different curve. What is really so important is the range of the wave numbers. Remember that the wave number is related to wavelengths. In a dielectric, for fixed frequency, the range of the wave numbers is limited. In this hyperbolic system, it's not. The hyperbola runs forever, so this range will also be indefinitely extended. You may ask, why did I put hyperbola this way and not that way? Well, both can happen depending on which permittivity is positive and which is negative. So either this or that. That's the case of hyperbolic materials, but in both cases, you have high wave numbers. That gives you explanation of why they looked like normal metal, like metals and dielectrics. Well, depending on which one you have and which side you look at, if you have this situation, light can, the range that, of the wave numbers that your eye can detect is the range of wave numbers which are supported by the air, and it's limited. So you only see this, when you look at it, you see this range of wave numbers. Here you will see nothing. It's like metal, so it's now light can propagate through this. And here it will be like a weird dielectric. Yes, the shape is different, but light is still coming through. So maybe metal, or something which looks like metal, maybe dielectric. But there is a big deal there. So if you look at, remember this picture, the reason you see those rays, in order to see something, light has to come up into your eyes. So this ray goes from the sun to the shrubs. It gets there, but somewhere there is some dust particles. And those dust particles scatter the light into your eye, like here. And what determines what you can and cannot see? There's just one scale, one of something with dimension of the distance in the electromagnetic wave, and that's the wavelengths. And it is this wavelength which determines the ultimate limit which are possible by optics. How much you can resolve, what is the smallest scale that you can resolve with an optical microscope? How tightly you can focus the light, and so on and so forth. It can, can be put in this straightforward mathematical form referred to Abbe, but three people, Lagrange and Helmholtz, and Abbe himself contributed to that. The important part is this NA, numerical aperture, is related to how good is the lens, goes all the way up to unity, And the body peak part is half of the wavelengths. But look at that. This wavelength is related to inverse wave number. If you can support infinite or very large wave numbers, your effective wavelengths can be very short. So that means there is no limit.
What does that mean?
It means buckle your seatbelt, Dorothy, because Kansas is going bye-bye.
So here's what it means. If you use hyperbolic materials for a microscope, the conventional resolution limit for optical imaging will not apply. You can have a visible light microscope with X-ray resolution. If you use hyperbolic material, you can have the light can be focused to very, very small scale, much smaller than the wavelengths, or arbitrary small spot in this simple picture, but really subject, of course, to the atom size constraint, because at that point we cannot talk about material response. There is something also very important. In conventional textbooks, we talk about forbidden and allowed transitions. They're based on some quantum mechanical rules. But there is a major ingredient, major restriction there to all those rules. That assumes that the electromagnetic field does not change much on the scale of your emitter. And with these high wave numbers, with this so tight focusing, we can break this assumption, and the forbidden optical transitions will no longer be forbidden. And there is another thing. We can think about rate of our devices like light-emitting diodes being limited by the rate of spontaneous emission, which we think as something which is limited by quantum mechanics and the material properties. But using hyperbolic materials nearby in the environment of LED, in the design of LED, we can accelerate it dramatically, way beyond what is currently possible. So there are new devices and a lot more. So before we go to that, after all these possibilities, let's think about whether this realization is really whether they are practical. They are. If you make a multi-layer metal dielectric structure, that will give you the desired anisotropy. And we can have some materials of that kind in all different wavelengths. And one of the first came from Purdue in the visible and infrared spectral ranges by fabricating the groups of Vlad and Sasha Boltaseva later. Doesn't have to be layers. It can be nanowires, and different groups focused on this design. And here's an example of the nanowire composite. Some natural materials will do that as well. Bismuth has very anisotropic Fermi surface. So this anisotropy will translate into different electromagnetic response. And there will be a range which was known for a long time, actually, since 1960s, that there is a range of frequencies where one permittivity is positive and the other is negative. So it shows hyperbolic response. Or you can use high-quality dielectrics. Because what happens is some of them are polar dielectrics, so there is some redistribution of electron charge. Some atoms grab more electrons, and some end up with less of electron density. So when they start to vibrate, there is a vibration of the electron density. And that gives rise to the permittivity. So again, there will be a range. In this case, it corresponds to mid-infrared frequencies, where the response is hyperbolic again. Note to make, those hyperbolic materials are only hyperbolic in some finite range of frequencies. I showed you all the beautiful pictures of different hyperbolic materials, but they are hyperbolic in different frequencies. Bismuth is in terahertz, sapphire is infrared, and those metal dielectric composites are invisible. And the natural ones, now people studied a lot of them, and the horizontal line is the wavelengths, free space wavelengths. The rainbow shows the visible range, and lots of them are here, which show the hyperbolic response. Note that the visible light regime is covered by two materials, which are now really popular in the study in physics, because they are also topological insulators. But they also show this. So the people who study them mostly study them for this purpose, but they're also good hyperbolic materials. And if you study the entire spectrum of electromagnetic waves, you find that examples of that you can cover the entire range. Especially interesting is this hexagonal boron nitride because of really high quality of those crystals that went that were initially developed as substrates for two-dimensional materials such as graphene. Here's an example of this is experiment coming from Columbia University, a group of Dmitry Basov. They used flakes of those hyperbolic hexagonal boron nitrides and excited different mode patterns. And so this picture shows the calculation, but they actually did measure the profile of those modes by some rather interesting means. They put a metallic contact and close by, kind of to scatter light, and then determined how much light was scattered depending on position, and got images of this. So what they observed was that the light in those materials was localized at the scale of wavelengths divided by a factor of 500. You break this limit by more than 2 orders of magnitude of hyperbolic materials. So that brings me to the argument in favor of my second point, that light in a hyperbolic medium can be focused in an arbitrary small spot. If you want to have imaging, all you need to do is something which will be capable of super resolution and magnification. To get super resolution, all you need to do is to be able to resolve it, to use hyperbolic material which supports those waves, and then you need to introduce curvature, like to make a lens, so that you can get magnification. And that was indeed the idea of this work on what we call the hyperlens. It came out simultaneously into groups, our group and the group of Professor Ngeta, both in 2006. So, of course, for theorists, everything is a spherical cow. So instead of a lens, which would be really this part of the device, we considered cylindrical or spherical system, which was easier to describe it. But the field in the relevant part of it looks like that. So if you have 2 point sources very close by, the light will get in this hyperbolic system. So these black lines are metal parts. The yellowish background is a dielectric. So it's multi-layers in a curved geometry. And the light from those 2 point sources will come out and will propagate without broadening, without diffraction, because there is no diffraction in hyperbolic medium. Will propagate out, and outside, out here, these beams are now well separated. And then, if this distance is larger than the wavelengths in the free space, you can image it, you can see it with your eye. Well, your eye will not have that much magnification, but then you can use normal microscope, and then you can see it. So that's indeed how it was done, except that they did, of course, didn't use a spherical cow. They used the actual lens with half of the cylinder structure, and it was observed. And later, these structures were developed in different frequencies, for different frequencies, in different areas. Even the concept was even extended to ultrasound imaging. And that's how I just put the number of papers which showed up about, which were written to further improve this hyperlens and use it for different applications and different frequencies. One of the recent examples is to use it for lithography. So if you can magnify, you can also demagnify. So you have a mask on one side, and then this hyperlens will demagnify it and allow you to make an image, to fabricate a structure with really small scales. So that's how it will work. And light propagation, something that I started with, will also be very different. And one thing you need to remember. In all anisotropic materials, propagation is highly non-trivial. You can look at this beam. It's kind of general feature of anisotropic materials. The direction of the beam and the wavefronts are not aligned with each other. So this direction of the normal to the wavefronts is related to phase velocity, but the direction of the beam is the group velocity. Group velocity is given by this equation. Omega is like free energy for light, k is like momentum, so it's usual expression for group velocity that you find in any textbook. And this thing is normal to this hyperbola. So see what happens? The group velocity goes this way, the wave vector goes that way. So if you have light incident on your material, the beam, the phase velocity are normal to the interface, normal to the wavefronts will go this way, but the beam itself will show negative refraction. Remember that picture I showed in the beginning? That's the explanation. But can you do more? Well, one disadvantage of the hyperlens was that these curved surfaces, which are hard to make, And then you have to put an object which you want to study, you have to put it in here. So why can't we use a planar structure? Yes, we can. But in this case, instead of doing this direct imaging, when you eliminate object first, and then focus light on the screen and on your eye by this lens system, you do it differently. You first structure the incident field, then have the structured light incident on your target, and then image it. Of course, the image will be complicated, so you really need to compute it to reconstruct it. But this way, you can do something interesting. Again, remember our hyperbola. Remember the idea of group velocity. If I have a point source excites all waves with all wave numbers, and then the hyperbolic material will excite very broad range of wave numbers. And group velocity is the normal to the curve. So see what happens? For the light here, the directions of the velocity will be different. This will give you the usual behavior. But far away, this hyperbola asymptotically approaches a straight line. So all the directions of the group velocity will be the same here and in no other direction there. So you will see light out of this point source and hyperbolic medium going either this way or that way. And those beams, again, they will be various subwavelengths. You've seen that already, and they're not diffracting. And in fact, not only they are there, but they're also very strong in intensity, to the point that a group of large alive actually used that in experiment, this behavior in experiment, to use a real nanolithography and use those beams to make subwavelength, very small patterns in the photoresist. They are there, and they can be even used as a fabrication tool. But remember the other thing which I told you? There is this frequency dependence in the properties of hyperbolic media. What that means is permittivity is changing, so this hyperbola, which I keep showing you, will change as a function of frequency. So for red light, it will be like this, for green light like that, and for blue light like this. So that will be the pictures in the real space. That allows you to image like this. So imagine you have the substrate, and you illuminate it with white light. So different frequencies, different colors will go in different directions. So see, this is how it's going to work. We are going to to have a point source, maybe some hole in the mask at the bottom, and the light goes in different directions, illuminates this object. In this case, I have 3 tiny balls. Think about them as viruses or something else, and then change the wavelengths. Maybe use white light, maybe just continuously change the wavelengths. See what happens? You scan the sub-wavelength illumination point like a searchlight that is scanning the surface. And you can do it in parallel, like this. So this is an experiment which recently demonstrated this behavior. There was this hyperbolic material substrate. There was a small hole for illumination. And then was a nanowire sitting here, which was positioned at some angle. This is the image. The image is quite broad. This thing of the order of wavelengths, see? You don't get super resolution, but then you see the different colors. And you know in advance which color went which direction. So you can know precisely where this point was and where that point was. And it gives you, in the resolution that it gives you, is comparable. If you have two, in this case, we have example of two wires in parallel. It is comparable in resolution to scanning electron microscopy. I think I'm boring you. Hope. Let's have some fun. So I call it Nana CAT scan. If you Google CAT scan, that's the picture you get, first thing. Of course, most of the time there will be medical things, medical machines. But some of them, well, they were actually scan cats. There are 2 possibilities. Scan a cat in a CAT scanner, or scan a cat in the scanner you have in your home or in your office, which is a xeroscope. Well, and then there is the community who put this, who go all the way, who literally scan their cats and compare the scans. I'm not sure what they do with them afterwards, but they post them online. So you see those different scans of different cats. So if you have a nana cat, we can image it by using this approach. So instead of a Xerox scanner, we'll use the hyperbolic substrate. We'll change, depending on the direction where light is going, we will get different information. And in this case, the cat is not transparent. You only illuminate its bottom part. But you can still learn something about what cat is from those cat scans. So that's another way of doing microscopy with super resolution. In case if you don't want to make complicated structures shaped with incurved geometries. There is another thing which is big about hyperbolic materials. Again, this elliptical thing, it has finite size. This hyperbola has infinite size. Clearly, the hyperbola will support a lot more waves than a simple dielectric. We characterize this by the idea of density of states, which is related to the phase space, to the volume in the K space. And in this volume, again, this picture is taken from a textbook. You saw it first when they derived the Planck's law for you. You count you get the volume in the space of the wave numbers, divided by the volume of a single state, this cube. Then you have the number of states. You take the derivatives. That's the density of states. Why is this important? Imagine you want to kind of first idea of quantum world is something like probabilistic process. They will give an example, I don't know, like probability of winning a lottery or probability of winning in a slot machine in a casino. And of course, it's very small. But as in quantum mechanics, if there is two factors, there's probability and there's how many ways, how many different ways, how many times you can play it, how many different states you can use. Yes, the chances of winning is small, but if you get lots and lots of tokens, and if you keep play again and again for free, then you can win eventually. So the number of so in all quantum mechanics, it's all about probability amplitude, which is quantum mechanical number, and the number of states you can take advantage of. The more states you have, the larger the density of states, the stronger will be that transition. And in dielectrics, this volume is finite, but in hyperbolic materials, remember this hyperbola running. It's formally infinite. There will be a cutoff eventually. You cannot go to the wavelengths which is smaller than the size of the atom or the unit cell of your structure, but it's far. And so it's infinite, formally infinite, and it's even better because, well, I missed that part. It happens at every frequency of hyperbolic bandwidths. You have infinite density of states at given frequency. You change the frequency, permittivities change. But it's still hyperbolic, it's still infinity. So infinite at every frequency. I like this play of words because it's similar to the popular book of Dangers at Every Speed, which made a big splash in America at some point. So density of state, to give you an example, I don't want to go in many details. This is the thermal energy density, and here's the density of states up there. And this is a great endpoint. It's so fundamental that it will affect all lots of different properties. And I give you 3 examples there of showing the proof of principle, improving the radiation decay rates, and even use it to improve the performance of quantum light coming from diamond centers. Know that those breakthrough experiments come from Purdue, from group of Vlad and Sasha Beltaseva. All right, what else? Let's keep things fun. So how about making something which is darker than black? Well, it's something that you do all the time, or if you need eyeglasses, because you don't want light reflected from your eyeglasses. You want as much light to go through the eyeglasses to your eye, right? You want to reduce reflection. So what they do, they put anti-reflection coating on your glasses. And what do they tell you if you wear eyeglasses? Don't scratch it. Here's some piece of special cloth. Use that to clean your eyeglasses, because if you don't, you will damage this coating. Makes perfect sense. You work so hard to make this thing well, and so don't damage it. I want the exact opposite. I want something which will work in such a way that the more you damage it, the better it works. Well, when you have damage, there will be scattering. And some scattered light will go up, and some scattered light will go down. And remember the story that I told you? It's all about the probability and the number of different ways. The probability and the density of states. Density of states up there is what you have in the air. Density in states in here is what you get in the metamaterial. And in the hyperbolic medium, it is infinite. or formally infinite. So, very easy. Take one of the samples, which you people already made, and damage them. So put them in the polishing machine and make all, put the wrong values into all the controls so that instead of polishing it, it will be damaging the material. Make lots of roughness. And what do you see? This curves 1 and 2 show reflectivity before the depolishing the material. And once you do that, reflectivity goes down to 0. And in fact, an experiment up to 30 degrees, it was within the noise level of the measurements. In a very simple way, it works so well. So that experiment was done by the group of Professor Narimanov at Norfolk State University. So darker than black. Interestingly, after that paper, the most interest I got about that was from some companies who were interested in making something like cosmetics equipment, so make very dark eyelashes, or I don't think it will be, those materials will be particularly healthy. Possibly. And finally, so I talked about these examples and better light emitters. So again, if you have, this is the idea of hypercrystal. I will tell in a minute what it is. If you have quantum, if you have emitters, if you put, put some emitting layer, if you put some emitting layer here with quantum dots, and then you put a multi-layer structure or other structure which is hyperbolic, and then you need to outcouple light. So that's the crystal part. So in this case, it's simple one-dimensional periodic pattern, but you can do better. You can make a pattern like this, which goes deep into, so this is the original structure, active layer, hyperbolic thing, and then from the top you drill holes through that. So you better out, instead of something which just sits on top, you have this outcoupling structure throughout the whole material. And what you do from this, this is the different, shows the light emission from different areas of that device, of different devices there. Different plots, different pictures correspond to different distances, different patterns of the holes here. But if you compare this light coming out of that from this, to the light coming from the same emitter at the same pumping, but without the hyperbolic structure, the intensity goes up by 2 orders of magnitude, and the speed, how fast this light goes out, also increases by a factor of 20. So yes, you can have your cake and eat it too. Usually people think about those things being in trade-off, but hyperbolic materials allow you to break through those limitations which were considered fundamental. And at this point, in the last few years, it crossed from the state of being potentially useful for some devices into something which is now used as experimental tool in a lab to study different phenomena. Now there is lots of active research into studying two-dimensional materials. The more we learn about them, the better we understand them. And optical measurements give you lots of information. Unfortunately, well, it's two-dimensional material. There are not so many atoms, and some transitions are weak. So yes, they produce some emission, but it's so weak it's hard to detect and hard to get reliable numbers. We need to enhance it. All you need to do, you take this material, which you want to study, put onto this hyperbolic material, and the light intensity immediately goes out, so then you can study the light coming from this. This is just kind of like an amplifier. So at the moment, people are already using it as a tool. And this is artist, so that was a real experimental picture. That's an artist view of that. So I think I used lots of time. So you can have lots of fun with the physics of those structures. This is not an artist view. So this is a cylinder made of hyperbolic material with some distribution of permittivity. I don't want to go in details there. It was made in such a way as to support light trajectory like this. We just wanted something really crazy there. That's real calculations. That's what it will do. There is light beam incident here, and that's what, notice that how small this is the wavelength. The device is quite small, but still, it's even though it's a nanostructure. See how closely this classical trajectory resembles the beam, which you can make light beam do something like that. So I would like to conclude on two things. So first, I would like to acknowledge the people who really made the key contribution, which made it possible for the field to take off. Our theoretical group, Viktor Podolsky, he was my postdoc when we started that. Viktor was actually a student of Vlad. I was a young professor at Princeton at that time. I hired him. He just graduated from Vlad, and I hired him to do some completely different things. And he taught me about this field of metamaterials and all the possible excitement that we can have there. So, eventually I made the jump. I changed the fields. And that was, in the very beginning, it was Vlad's results, like first demonstration of negative index and a few others, which were really critical for me to understand what happens in that field. And then, if you've seen several times, in the key experiments that I showed you, all experimental data that I showed you, of course, were not mine. So some of them, quite a number of them, came from Vlad's lab. Claire Gmacher, experimentalist at Princeton. Remember I told you about negative refraction hyperbolic materials? That Nature Materials paper was the first experimental proof that something great, something unexpected will come from hyperbolic materials. Xiang Zhang, he led the effort on first experimental demonstration of the hyperlens. Mikhail Noginov, remember data on darker than black material, and he did also first demonstrations of nanowire metamaterials. And Vinod Menon, I met him when he was a postdoc at Princeton. He is now faculty member in City College in New York. He did the experiments on this hypercrystals and the active thing. But most importantly, I would like to say a few words about those two guys. So Victor was my postdoc, and the two students who were there in the very beginning, Zubin Jacob, who is of course not a student, he went anymore. He went, after graduating from Purdue, he went to Canada as a faculty member in the University of Alberta. But then, after being very successful there and getting tenure there, he moved back to alma mater. He is now a faculty member here at Purdue. And Leo Alexeyev, who, you see those guys put some whiteboards. You notice this equation. I showed it several times. Hyperlens HUP is not visible, but I think, yes, you see the part of that. But Leo went to Silicon Valley. Became a data scientist eventually. This beautiful view there is also related to the talk, to the current presentation. That picture was taken in Bahamas in one of the first metamaterial conferences. And that's where we went to present this work for the first time. And that's where I made a big splash and convinced people to go after it. So this, I think, is something that will probably, and the theoretical work, and especially the experiments by this group of people, is what made this progress possible. Finally, a few words about what I see in the future. We have this big disconnect between two our main technologies of that time, the photonics and electronics. When we do computation, we do it with electrons. And when we send information, when you place a phone call on your cell phone, very quickly it goes to the cell phone tower and then into fiber optical networks. This information, when you call Europe, it propagates in the fiber optical network most of the time as light. So those things work great, but they don't work great together because there is a fundamental disconnect. The electron is very small. I mean, that's why people thought about this particle for so long time. Its characteristic scale is about the size of its de Broglie wavelengths. It's an angstrom. The size of the photon is on the order of wavelengths. It's about a micron. Micron, angstrom, factor of 10,000 difference. It's not easy to interact one world with the other. And when you want this interaction, you have to work really hard to make it strong enough. And that's one of the issues that that's a major constraint in quantum computing, for example. What these hyperbolic materials allow you to do is to build a bridge between those two worlds. because hyperbolic materials, they are optical materials. In the entire presentation today, I was talking about light. But they are not restricted to being so large. They're not restricted to propagate in beams which are 1 micron or more across. They can be really, really tiny. And when they're tiny, they can strongly interact with electrons. And as I told you before, this part is still not done. You can break many rules of this. You can unforbid many forbidden transitions and finally make the strong interaction of electrons and photons possible and build the bridge of those worlds. Not going to happen in the next 5 years. Even in the cases of the greatest successes in technology, like laser or transistor, it took 50 years from the moment when people understood semiconductors to the moment when the integrated circuit became ubiquitous in the world around us. Laser was successful much faster, but even with the laser, in the first years, it was called a solution looking for a problem. So I hope that these hyperbolic materials will become really important components bridging of the photonics and electronics, but it's going to take quite some time. Thank you.
So as mentioned, Evgenii is very broad, so any questions in history, legal issues, or hyperbolic metamaterials? Yeah, Arden.
Well, it's hard to ask a question after a presentation like that. I pointed out it's hard to make a question after a presentation like that. But you're working in a realm where you have two types of wave functions. One is the electrons and the other is the phonons. And of course, the phonons can overcome the Coulomb barrier, so you can also have nuclear interactions as well. How does this play a role in metamaterials, many of which are two-dimensional? And how do you discriminate between photon scattering and other types of scattering in the range you're working?
The question is about this separation of different scattering phenomena in metamaterials. It's actually a very deep question, because at some point it's not straightforward to see where the boundary between photon and electron, or even a phonon, is. Because we can, I'm sure you have heard the word like polariton. That's a kind of combined motion of the motion which combines the vibrations or the response of the medium, maybe electron cloud, and the electron which moves there. So I showed the picture of sapphire, and there the hyperbolic response, where is it coming from? It's electromagnetic response, but it comes from the fact that there is this unit cell, there are different atoms with different, they have different charge distributions, and when they vibrate, these charges move around. So what you have simultaneously, light, which excites that motion, electron charge, those bound electrons, which couple light to the material, and the vibration, which is phonon. So it's actually a very deep question. And in fact, the thing which I was talking about, when I was saying we are going to build a bridge between photons and electrons, what the bridge really means, it will be a state precisely about this joint wave function of electron and light, which will be neither pure photon, neither pure electron. And that's what the idea of strong interaction is. Weak interaction means it's mostly, it's like electron, which sometimes scatters. You see that it starts, and you follow its track, it moves straight, for example, and then you see it change the direction. So, oh, it interacted with something. It's small scattering. But when you have really strong interaction, it's no longer the case. It's neither one nor the other. The way I would see it, it's what I was really hoping for, is to get precisely in the regime what you're asking me kind of how to avoid it, when there is no boundary between them, when this system is operating on this, we call them quasi-particles, which combine the properties of both things and hopefully allow us to take advantage of the both worlds. It seems to be too good to be true, but in this presentation, I showed you several examples when, yes, you can have your cake and eat it. Yes, you can have a device which is more powerful and faster at the same time. Again, there was no, to my knowledge, there was no experiment conclusively proving strong coupling in hyperbolic materials. That's still something for the future. But that, I think, when the home run will happen. Because it's, again, if you think about the biggest breakthroughs like laser or transistor, do you know, or even into some, let's not be so physics-minded, let's talk about some applications, I don't know, like integrated circuit. Do you know, so when Intel put their, disclosed their 4004 chip at an exhibition, it was first real microprocessor. Do you know what application those engineers had in mind for it? A traffic light. What was the application for the laser they thought about? A ray gun or something like that. What happens, I found it's almost universally the case that the people who actually discover some new physics which they think be relevant never guess it right what is it going to be relevant for. Some of the smartest people in history appreciated that. I'm sure you know the story of Faraday. So when about electricity, when I read it in several different sources, and they differ about the details. So I'm not sure how exactly it happened. When exactly the words were, not because I don't remember, but because different sources report quoted some slightly differently. But presume it could have been a British minister, it could have been Queen herself, which I strongly doubt that she would go to Faraday's lab. But after being shown those interesting experiments, the question was, well, it's fine, but what is it really good for? And the answer was, I have no idea. But I'm sure that in 20 years you will tax it.
All right, speaking of cakes, you can eat it. Let's join us for this small reception across the corridor. And let's thank again Evgenii for this wonderful lecture.
Thank you.